We have a couple of short talks. Let's introduce, let's welcome João Lizárraga with the work Active and Chaotic Swarmalators. We have 15 minutes, right?
Okay, thank you. Well, thank you for the introduction. That's my name. I'm a graduate student in the University of Campinas. And I'm assuming that most of you don't know what a swarmalator is. But I'm also assuming that you know what synchronization is. So I'll make a very small introduction, very small. And I hope I can fit everything. And I'll start by splitting the word. Okay, so we have swarmalators, and it comes from swarm and lators, swarm oscillators, and oscillators can synchronize. That's it. Okay, so we have swarming, which is one type of self-organization, and we have synchronization, which is another type of self-organization. Swarming happens in space, and I'm sure you have seen this type of behaviors. You have seen movies of this everywhere. And the rules are easy, okay? So we will focus on this rule, at least for this short talk. And if we have a bunch of individuals distributed in space, we have aggregation. Okay, they will attract each other, but there is also a repulsion, because they don't want to hit each other. Okay, that's the idea. That's all we need to know about swarming for this talk. We also have synchronization. I hope you can see the hands clapping together. And the idea is that we have, again, individuals, and these individuals have internal degrees of freedom, or phases. Okay, and that's it. So they have phases, and we don't have amplitudes or anything like that. And after specific conditions, under specific conditions, they can synchronize. That's the idea. Okay, now that we know swarming and synchronization, we can talk about swarmalators. So a swarmalator is an individual that can move in space, but which also owns an internal degree of freedom. And we are interested in knowing about a population of these individuals. Because remember that we still have aggregation, and we still have synchronization, because they can move and they can synchronize. That's the idea. So what will be the behavior of this system? That's what is important for us. And also how positions will affect phases, or positions will affect phases, and how the phases will affect positions. Okay, these systems seem to be weird, but actually you can find several examples of these systems in nature. The first model introducing this idea of swarmalator was presented in 2017. And it follows these basic rules. Okay? There is an attraction, and there is a repulsion. Now, you see there is also this term here, which is the difference of the phases affecting the spatial dynamics. Now, the phase dynamics follows a Kuramoto-like model. So it's very simple, but in this case, the strength of these phase differences are strengthened or weakened by the distances between individuals. Okay? That's the only difference. And that's it. So with these three equations, x and y and theta, we can get these behaviors, these patterns. Okay, you see that we have, for instance, this case, the static synchrony, where they cluster together and they also synchronize, but we also have the static async here, where we have the cluster, but they are in async. The two, I would say, more important cases here, most important cases are these two, the active phase and the splinter phase wave, because these two are active, even though there is no self-propulsion. So this activity is a product of the interactions, basically. Now, the problem with this model is that it's too complex. Okay? And actually, there is a comment saying that the analytical results they got are completely different to the ones they got in the numerics. And there is also a one-dimensional equivalent of this model. And it's very simple because it follows the Kuramoto model. Okay, you can see that there is a sign here, there is a sign here, and the affection of the phases in the space is given by the cosine and vice versa. Now, the problem here is that the position is confined to a ring. So the states that we can get here are these. Okay, and you see it's very similar, but it's very limited. So we worked using this model, and we didn't want to affect distractability, but we wanted to recover the active features. And what we did was considering frustration. Now, if we know about the Kuramoto model, you most likely know about the Sakaguchi modification of the Kuramoto model. So we did the same thing. Okay, and we call this Sakaguchi swarmalators. That's the name. You can find it in Google. So we have phase lags here and here. Okay, and it's symmetric. And we got these behaviors, reactive behaviors, that you can see better here, if it works. Yeah. Okay, so you can see that they will keep rotating. You have the active phase web where the particles' phases are correlated with their positions. We have the asynchrony, and you have the asynchrony. Okay, that's nice. But, since this model is easy to treat analytically, we were able to find the regions where these states are stable. Okay, so you see, this is nice because you see that in this case, for instance, it's very simple. You have squares, and you know where each of these states show up, like the asynchronous is a square, the synchronous is a square. But when you change a little the coupling strength, the K, the shape is a little different. Okay, it changes, and it's not trivial. Same happens with this. You can see that this is not even a circle. And as you can see here, we pointed out like stars and circles and squares, and it's because we found new states. Okay, besides these active states, we found states like this that we call the ring states. Okay, what you have in your right is a scatter plot of the positions and phases of each of the individuals. You can see in the left that we have clusters, but it's interesting that we get these rings. We also have this state that we call noisy phase wave, where you still get the correlation, but it breaks. And probably the most interesting of these states, the one that we call the turbulent state. Okay, you see that in the left, there is almost no pattern at all. But in the right, you can see this kind of vortices. And this is very nice. And this is a state you can find in different places in this parameter space, as I showed you before. Okay, so good. We got the active states, but we are still missing a couple of things. We are missing first the second dimension because we are confined to a ring, and we don't have repulsion, right? So we lost this distribution of individuals in space because we don't have repulsion. If you think about the Kuramoto model, it's all attraction or all repulsion. That's the idea. That's the problem. So we managed to get this model. I won't try to explain this. But the idea is that we have two sides. We have attraction here, scaled by JA, and we have the repulsion side, scaled by JR. But it's the same. Okay, it's very similar. And we got the states that we wanted. You can see here, for instance, the point synchronous state is where we have too much attraction that they cannot distribute. They get distributed, basically. We have the distributed synchronous, where the attraction and the repulsion are balanced, so we can get the distribution. And we have also this case, where there is no synchrony at all, but we still have the distribution. Now, here, one of the features of this model, and why we use so many sines and cosines, is because we wanted to keep the tractability of the model. Okay, so we are keeping the periodic boundary conditions, but in this case, instead of confining the system to a ring, we are confining it to a torus. So, since it's tractable, we were able to get, again, the regions where these states show up. What's that? Yeah, but what I'm saying is that we're in a torus in space. Yeah. What's that? Chaos? Yeah, yeah. We haven't checked that. We got chaos here. That's what I'm going to talk about now, actually. But yeah, but we didn't check, really. We didn't get to explore that, basically. Yeah, yeah. We might, but we don't know. That's the honest answer, yeah. OK, so again, we found the regions where these states are stable. And we found something interesting that came actually from the numerics, that at some point, the system started to get crazy. Okay, and we found this. I'll show you 2 examples. Yeah, I want you to see to the right side. So again, this is the state of each particle in x, y, and theta. So the first time we saw this, we said it's nice and it looks similar to a chaotic attractor, right? So we thought that it could be related to that. And when we go a little more to the left, when it's stronger, when the disorder is stronger, we get this. Now it's cropped because it's from -pi to pi, so I had to wrap the positions, but I'll show you something a little better now. Okay, so we got curious about this, and we calculated if it's chaos, and it is. So I'll show you something after this. But to close these things, I wanted to mention the things that are open, because we explored several things, but the models are very rich. Okay, so for instance, this is an example. This is a pattern that you can find in sperm, but in many systems you can find this type of patterns under very specific conditions when you take some parameters to the limit, and that's something we see here. We haven't checked these states explicitly. We have checked only the states that can be solved, right? Where you can understand the stability, basically. But we don't know about this disorder here. We haven't checked that. So yeah, we can use the model to understand this type of behaviors. And this is how the chaos looks in the torus, in space, again. You are not seeing phases here. This is how the particles behave in space. And you see that the attractor looks, OK, this is a projection of the attraction because we have 3 times n dimensions, actually. But it looks like 2 wings, and then it gets completely destroyed. But this is still chaotic. And I can show you that here. Yeah, this is a plot of the Lyapunov exponent, the maximum Lyapunov exponent that we calculated. And you see there is something very interesting here, that when we start to get chaos around here, there is still correlation between x and y. But then after a change of this attraction parameter, we still have correlation in the whole system, but there is a breaking in the correlation. So are we talking about synchronization of chaos? That's something we couldn't answer. We didn't deepen into that. We found actually the Lyapunov exponents for position only. And yeah, it shows that there is a transition after this about 2, basically. Was that? I'll finish now. Thank you. So another thing that I wanted to mention is that when we work using synchronization, when we talk about the Kuramoto model, for instance, we always think that this is an internal degree of freedom and that we don't necessarily have to see how this behaves. But what if we consider that this is actually a spatial periodic degree of freedom, right? So this is one of the movies we made, considering that the phases are actually the radius, and we use the spherical coordinates. And the behavior is very similar to behavior found in mosquitoes. Okay, in mosquitoes, you have that males cluster in the middle, and females like rotate or move around these males. And it looks actually like this. And they also show synchronization and stuff. And before I finish, I have to mention that all these results were obtained in collaboration with Marcus, who's my advisor. And that's it. Thank you.
All right, we have 2 minutes for questions.
Hey, nice visualizations. In your, when you define the model, why do the phases depend on 2 indexes?
Where?
Go back, I think the last model you showed. At this side.
Oh yeah. Okay. Okay. Sorry. Yeah. This is just a way we wrote the model because it was too long, but it's actually the difference. Yeah. It's xj minus xi.
Okay.
Yeah.
Okay.
Yeah. I'm sorry. That was
and
something missing.
about the mosquitoes, what will be the phase of a mosquito?
Oh yeah. We actually consider, at least for the movie, we consider that the phase is the radius. So you see here, we are considering that x, y, and theta are the spherical coordinates, actually.
Ah, okay.
Yeah.
Okay.
So theta is the radius, and you see that the ones closer to the center are the ones with the same radius, basically.
Okay.
Yeah,
Okay.
the same phase.
Okay.
Yeah.
Thank you.
Questions?
Oh my God.
Okay. You cited frustration right in the beginning of your equations. Where exactly are you putting frustrations in your equations?
Okay. That's a good question, actually. We got when we were about to publish this thing,
Yeah.
we got a similar question because, yeah, there is a problem with the definition of frustration. Yeah, we were actually asked to use disorder instead of frustration. But frustration is a word used in the Sakaguchi-Kuramoto model. And it's basically this phase lag, which is called the frustration parameter. Okay, so in this case, if you see the Kuramoto model, you will see only this thing without the cosine. But yeah, we added the cosine because that's the effect of the phases in the position. And we added also this lag in the phases. Right? So that's the frustration. But yeah, I know it's not like a good word to use in this type of systems in front of physicists. Yeah, thank you.
Okay, thank you.
A last question?
Just a question. Do you have in mind if for the simplest case of motion on a ring, there is some natural example of this?
Oh yeah, that's something actually we're working on. You see this type of behavior. Yeah, I'll use this one. Yeah, this type of behavior can be seen in sperm. That's why I use this actually. You see these rings are actually clusters of sperm. So under specific conditions, sperm tend to make this behavior, and you have many of these. And in each of these clusters, you can find this correlation between phases and position, an angular position, which is basically the ring moving that I showed in the model.
Just a suggestion, sometimes in ants, in experimenting with ants and lab, you can see this kind of patterns, ants moving on the ring. Maybe we can discuss it.
Yeah, sure. Yeah, thank you. Yeah, one of the problems is that, and we tried actually to recover this dynamics, is that we are losing completely the radius. So when you see ants, for instance, at least what I saw is that you don't have a ring. You have like a vortex, right? So they have different radius.
Yeah, but in a certain way you can impose a ring
Yeah.
keeping some
Okay. Okay, got it. Thank you.
All right, so let's take this
Okay, good.
picture again.
Thank you.